So hello guys, welcome to our next video in the channel GS and Google Earth Engine. So in today's video, we're gonna do some indices like the SAVI. So it's also called as Soil Adjusted Vegetation Index, or it is also called as OSAVI. So basically, the Soil Adjusted Vegetation Index is developed to minimize the influence of the soil brightness in the areas where there is a sparse vegetation cover. So like for example, the NDVI get saturated upon the extraordinary the green covers. So we need to go for some kind of parameter where we can adjust the soil parameters. So we have to introduce some of the soil adjusting factors. So the SAVI, or the Soil Adjusted Vegetation Index, is the one which helps us to do this. So the formula for calculating the Soil Adjusted Vegetation Index, or SAVI for short, will be shown shortly. So here you can see this is the formula for calculating the SAVI index. So if you can see the formula, it is more or less similar to the NDVI. It is using the near infrared band, red band, as a normalized difference. But one addition factor is that we have the L factor now, which is added in the denominator as well as multiplied with the addition of 1. So what does this L factor do is that it is a soil brightness correction factor. So it is typically, its value is 0.5 for most of the intermediate vegetation covers. So but for with the a change in the Landsat or the Sentinel satellite images, so you can see the change in the value of the L as well. So typically, for using with the Sentinel-2, the 0.45 or 0.42 is the ideal Sentinel-2 L factor value for the SAVI. So as you can see, if the L value is near to more or less 0, so it is like that, it's a NDVI image. Or it is near to 1, then it's more that the influence of the soil is more in there. So some of the key points which you have to note while calculating the SAVI is that the SAVI will modify the NDVI by using the L factor to reduce the soil noise. And when the vegetation is dense, the L will be nearly equal to 0. It means the SAVI is approximately NDVI. When the vegetation is sparse, then the L will be more or less equal to 1. It is better to correct for a soil background. So it is mostly used in the arid as well as the semi-arid regions. So in the agriculture and land cover monitoring also it's used, and it's also better for vegetation discrimination in the areas with exposed soil. So in that such cases, you can go for the use of this analysis. So let's start with the Google Earth Engine. So let's import our Sentinel-2 dataset. I'm searching Sentinel in our search data catalog. So remember, you have two Sentinel-2 images. I'm using the surface reflectance one. So you can just import it and rename it as S2. So for today's video, I'm taking some region in the Saudi Arabia because it's a mostly arid region. So I'm just selecting some of the dry regions in the continent. Just draw a rectangle, or you can draw any polygon if you want. So you can rename it as region of interest. My region of interest is ready, my image collection is ready. So I want to now create a variable called filter, because I want to filter my Sentinel-2 dataset. So take the Sentinel-2 and use the function filter bonds to region of interest. And you can also use the date in order to have the latest satellite imagery. So I'm using dot filter date to 2025. Let's say February, because it will be mostly arid from February to March. So you can take February to March 30. So remember, the end date in the dot filter date function is exclusive, so it doesn't take the end date. So you will get all the images from 2025 February 1 until the last image of 30 March 2025. So I want to also reduce the cloud cover, so I'm using dot filter dot filter. So boolean function dot less than, I want to reduce the property which is called cloudy pixel percentage. in the Sentinel-2. So just write cloudy pixel percentage or percent. So let's just check. Go to the description, image properties. It's a cloudy pixel percentage. So just copy this and paste it in here. So I want to have a cloudy pixel percentage less than zero point 0.1. Let's just print this and know how many image collections are available for this particular filters. So we have 13 elements available. I think that should work. So I want to scale my images also. So remember, you have the scale value for Sentinel. Go to bands, and here you will find, if you just swipe it to right side, so you will get the scale value of 0.0001. So you need to multiply all the pixels with the 0.001 in order to get the appropriate reflectances from your images. So just close this and create a one more variable called scale, because we are scaling the image. So for the filtered function, for the filtered image, we need to map a function. So use the function dot map and create a function which will take a image as an input, and it will return image, but it should be multiplied with 0.0001. That's it. So just take a median of it and click to your region of interest. That's it. Now our sentinel image is ready for our region of interest. We have multiplied with the scale value of 0.0001, and we have taken the medium composite of these 13 images, and we have clipped to our region of interest with the use of dot clip to our region of interest, which we have created as a rectangle earlier in this tutorial. So now we have the image ready. So now we need to calculate the MS, not MSAV, just SAVI, the soil adjusted vegetation index. So I'm creating a variable called SAVI. So how to do this? So here you can find my scale image is there. So we have a function called dot expression. So just go to documentary and search for expression in order to how this expression works. So here we'll find we are applying expression for an image. So you should go to ee.image and go to this expression. So here we'll find the description for the function. This will evaluate an arithmetic expression on an image, so it is possibly involving an additional images. So here it will apply all the available blends. The expression will be applied to all the available blends, and what you will have to give is that the input is the image, and you have to give the expression, and you need to map a dictionary, because whatever the values that are given in the function, it has to be provided as a dictionary. So now I have the expression, so I want to write down it. So you just write the expression in the strings, because it has to be a string. The expression has to be a string, and then we need to provide a map function in a dictionary format to interpret what the expression contains. So here you will find an example, x is equal to a plus b. You have to define what is a and what is b. So now here you will also find the expression should be a string. So remember the data types, the string, dictionary, the whatever the data types are. So please use it carefully. So now I have to go back to my function. Here you will find this is my uh, the formula for calculating the SAVI with the L correction factor, soil correction factor. So I need to first subtract the near infrared from the red band. Next, divide by the same. So near infrared, my plus red band. I think I need to add plus L correction here. L. So remember the value for L in the SAVI formula is 0.45. So I'm directly giving the value 0.45 for correcting for the L band. So here you have 0.45 to be your L soil correction factor for the Sentinel-2, and additionally I want to multiply with 1 plus L. So again open the brackets, add 1 plus 0.45. So if you can just go to Google and search what is the Sentinel survey formula for Sentinel-2, here you will get. So it is the 0.428 is the value for the Sentinel-2. So you just come in here and you make it 0.428. So here also you make it 0.428, or else directly you can have 1.0.428, something like that. So after all this, you can have one more bracket in here, because the multiplication is for the whole denominator as well as the numerator. So now my expression is ready. So here you can see in the numerator I have the near infrared subtracted by the red band, and the near infrared has addition added with the red band, as well as 0.428 correction factor has been added, and the whole expression is multiplied with the 1 plus 0.428. So now my expression is ready. You just give it a comma, and I need to map what is I have defined in my dictionary. So remember, it should be a dictionary. Whatever you have specified in the string in the above expression, it has to be interpreted by the expression. So my NIR stands for my scaled image, out of which you select B8, because B8 stands for the near infrared band. So here it should be a list, because we are selecting a band. So after that I should define my red. So again my scaled image, from the scaled image you select B4. B4 is my red band. So if you don't know about the band combinations, you can go to the dataset, Sentinel-2 dataset, and here you will find the band name as well as the description. So B4 is red and B8 is near infrared. So I think rest all is defined there itself. We have the near infrared, we have the red band, and both are specified in the denominator also, and we have the constant of 0.428, and we also have multiplied with the 1 plus 0.428. So I think the mapping is also done. So the expression is ready. We have the survey ready. So now I will just print this, print the survey, in order to know has it worked or not. So here you can see in the console we have one image with one band. So we have no errors. It has one band, so it has renamed it as B8. So if you want, you can also rename it as SAVI if you want, and give it a run, so that your band name will be renamed as SAVI. We have some internet issue here. Sorry for the disturbance. Yeah, click on the run now. Yeah, we have one band. Here you can see the name of it is SAVI. So it has the data type, dimensions, the origin. So it's CRS, everything is there. So our SAVI, the survey is calculated and printed successfully. So let's just add it to map.add layer, SAVI. Leave the visualization parameters like minimum, we'll modify it later. So minimum 0, maximum 1, and give the palette. I'm starting the minimum value from 0, because it doesn't have any kind of water body in here. It's a completely dry region. So palette, you can give it as a white, a dark green, or a light green. So remember to use the camel case always. The first letter will be a small letter, and the next word will start with a capital letter without any space. So it's called as a camel case. And next one is the dark green. So we have the three palette. You can rename it as SAVI image. Give it a run. We should have the map now. Yeah. So our map is loaded. So you can just go to the layer settings and stretch to 100% so that we can get the actual range. So the actual range ranges from 0.790 to 0.3. So click on the apply. Yeah, here we can see the index has worked properly. So wherever there is a low vegetation cover, there we have a 0, and wherever there is a dark green color, so it has some addition vegetation. So I think this is some kind of algae or some not needed vegetation, not important actually. So just it has worked. So wherever there is a high brightness in the white color, those are all a soil. So I hope guys you have understood how to calculate and execute the soil adjusted vegetation index in the Google Earth Engine. So if you can export with the help of export function, you can do that. So thank you for watching. If you have any kind of queries or doubts, you can always post it in the comment section. So thank you for watching.